Hello. In this video, I am going to show how to calculate the moment of inertia of this object, a disk with a hole in it that is off-centered. Okay, so let's see here. First thing we should do when we approach this problem is state our strategy for solving it. Okay, so basically, the strategy is as follows. I'm going to find the moment of inertia of the entire disk minus the moment of inertia of the hole. And in both cases, we're going to be rotating them about the center, this center of the disk. So if I rotate the small hole about the center, like that. So I'm sorry, I'm pictographically writing here is that the moment of inertia, which is black, the moment of inertia of the entire disk, or minus the hole, that thing there, is the moment of inertia of the entire disk, minus the moment of inertia of the hole around the center of the original disk. Now we can modify this a little more by breaking up this moment of inertia using the parallel axis theorem. So the parallel axis theorem says this moment of inertia is the moment of inertia of the hole about its center times its mass times the radius squared, the radius from here to there squared. So we can write this as moment of the entire disk about its center minus parentheses the small disk around its center plus the small disk at radius, and this would be R2 plus R3 around the center here. Okay, so that's more or less the pictorial strategy of how we're going to solve this. Okay, so the first thing we're going to do is I want to find the mass of the entire disk. So let's write that out. So the mass of the entire disk, even if it didn't have a hole in it, so the mass of the entire disk, if it didn't have a hole in it, would be greater than the mass of the gray disk because, well, it has an extra metal part that's in here. Okay, so mass, and I'm going to call this solid disk, or mass solid disk is going to be the mass of the entire thing, while just M will be the gray area there. Okay, well, we can find the mass of the hypothetical solid disk by saying it is equal to the mass of the gray disk, the original M, times the area of the solid disk over the original area. So original area, this gray area here is the original area. So we can write this out as the mass of the solid disk is equal to the mass times pi r1 squared over pi r1 squared minus pi r3 squared, where r3 is the radius of the hole. Okay, and of course then you can cancel the pi's, and that gives you the mass of this hypothetical solid disk in terms of the original mass. Okay, so the next thing we would like to know is what is the mass of the hole. So mass of the hole, we'll call that mass, I'll just be uncreative, mass hole is equal to mass, the original mass, times the area of the hole over area, which is equal to, so mass, let's try this way, mass of the hole is equal to M times pi r3 squared over pi r1 squared minus pi r3 squared. And then once again, you can cancel pi's. Okay, so now we have the mass of this thing and the mass of that thing. We can find their moments of inertia. Okay, so the first thing you want to do when you're doing moments of inertia of these disks is find their individual moments of inertia. You can do this with an integral, but in this video, I'm just going to look up the answer. If you look up on Wikipedia, the moment of inertia of a uniform solid disk about its center, you see that I is equal to 1/2 mr squared, where r is the radius of the disk. Okay, so by that token, this guy right here, the moment of inertia of that of the entire disk is equal to 1/2. Well, I don't know, actually, I can give this an example. We'll name that I solid disk. So I solid disk is equal to 1/2 mass of the solid disk, which is maybe we'll just write this in for now as mass of solid disk, which we know is this quantity here, but I'm just not going to write it in yet, times the radius of the solid disk, which is r1 squared. Okay, so that gives you the I of the solid disk. Okay, now we can find the I of the hole. So I of the hole, LE, is equal to, so we can do about its center is, the I of the hole about its center is 1/2 mass of the hole, R hole, which is the radius of the hole is R3, so R3 squared. And then we can have the moment of, then we have this term here, which is by the parallel axis theorem, it's the moment of inertia of the mass of the hole around the center of the disk. Right? So the way I'm putting this together is that the mass of the hole, imagine this is the hole and this is the center of the disk. So the mass of the moment of inertia of the hole about this center is the sum of two things. It's one, rotating this about its center like that, and the other, translating this around the circle. Add those together and you get the moment of inertia of this going like that. Okay, so the first one, this guy right here is just doing this. And now we're going to add the translating it, which is plus and 1/2, or not 1/2, it's just the entire mass whole times the radius it's moving around squared, and the radius it's moving around happens to be R2 plus R3. So the total moment of inertia of the hole around the center of the disk is mass hole, as this term here, plus mass hole times R2 plus R3 squared. Because this distance here, from here to here, is R2 plus R3. That's the distance from the center of rotation, the red dot, to the center of mass of the hole itself. Okay. So now if I want the moment of inertia of the gray object that we started with, then I can write that as, so I answer, the thing I'm looking for in the end, is equal to 1/2 m solid disk 1 squared minus this guy here, so I'm just going to write that out, minus 1/2 m whole R3 squared minus m whole R2 plus R3 squared. Okay, and now basically we just need to do some plugging in. We can plug in that into there and to there, and we can plug in that into there. Okay, so let's just write that out. So our answer is equal to 1/2 mass of the disk, which is R1 squared over R1 squared plus minus R3 squared times R1 squared minus 1/2 mass whole, which is this object right here. We can put that in there as, ooh, actually, I missed this M right there. Capital M there, 1/2 M. So now I'm doing this right here, 1/2 M R3 squared over R1 squared minus R3 squared times or minus this guy right here. So we have minus M R3 squared over R1 squared minus R3 squared times R2 plus R3 squared. Okie dokie. So now we can simplify this a bit. You notice all of these have a mass in them. All of them have this term, this denominator here. So we can simplify this answer a little bit. Answer is equal to M over R1 squared minus R3 squared times, well, this one will be R1 to the 4th over 2, that's a 4, R1 to the 4th over 2 minus, ooh, actually, I missed a term. This R3 squared didn't make it down. Here, R3 squared. So we have R3 to the 4th over 2 minus R3 squared times R2 plus R3 squared. And that, ladies and gentlemen, is the total moment of inertia of the gray object. Okay, so let's look through this. Maybe I can write this in slightly better handwriting. That was supposed to be an M. This is an R1. That is an R3. So both to the 4th. Okay. So basically what we have here, let's check the units. So we have a mass over meter squared, and each of these is meters to the 4th. So meters to the 4th over meter squared is meters squared. So it's mr squared. That's good. We can check some limits. Suppose R3 is 0, meaning there's no hole. R3 is 0. Then there is no hole at all. So then R3 is 0. Then this term is 0, this term is 0, this term is 0. We end up with M R1 to the 4th over 2 times over R1 squared. The 2 of the R1s cancel, and you get 1/2 M R1 squared, which is the moment of inertia of a disk without holes. Okay, so that's good. It does simplify the right answer. Suppose, let's do another one. Suppose that R2 is minus R3. So basically this hole is in the center, and R3 is equal to R1, meaning the R3 grows until it eats up the entire disk. So there's no disk left. Okay, so if R2 is minus R3, and this guy is 0, and if R3 is equal to R1, then this is equal to that. This cancels this cancels that. We get 0 minus 0, and we get a total of 0. So if there's no disk, there's no moment of inertia. Okay, well, that limit works as well. Okay, so few limits work, has the right units. I think it's a good answer.